Alright, you're welcome to today's lesson. This is Educational What's Laxing. My name is Jerry. So we'll be looking at the next lesson in our chemical reaction series, which is molecular choreography. Now, what is molecular choreography? Now, the speed at which chemicals react is very important to how they affect their surroundings. Even though iron rusting and hydrogen burning both involve electrons being exchanged in similar ways, one of these reactions is much more explosive. Now we'll be looking at the pace of chemical reactions in this lesson from probabilistic point of view. That means we are going to use probability to explain chemical reaction rates. Let's start the lesson. Okay, chemistry is all about the exciting ways that molecules can change and transform themselves. Sometimes the molecule can react on its own and break into pieces, but more often than not, chemical reactions occur between two or more molecules. Now, in order for them to react, they first need to find one another for the reactions to occur. Now, the time it takes for a reaction to occur depends on the details. If molecules are few and far between them, or if the reaction needs many collisions to occur, now the reaction will take longer to happen. So in this exploration, we are going to uncover the link between chemical reactions and probability to benchmark the kinetics of fundamental reactions. A few things need to happen for chemical reactions to take place between molecules. And what are those few things? The molecules, they have to be at the same place, at the same time. They need to be at a given orientation, and they need to collide with each other. And they also need to collide with a sufficient amount of energy. So not all collisions, not all molecular collisions leads to a successful chemical reaction. But for a reaction to occur at all, the molecules have to be in the same location. Most reaction takes place in a liquid or gas confined to a flask of fixed volume, and a molecule can be at any point within it. We are going to make things as simple as possible and assume the flask is like a chessboard with a fixed number of positions V that the N molecules can occupy. Alright, to get started, let's monitor the reaction at a position we will call site A. If we assume that N sugar molecules are randomly distributed throughout the flask, what's the probability that one sugar molecule is at site A? Now, probability is simply the number of sugar molecules divided by the number of possible positions those sugar molecules can occupy. And the right answer is this one, N over V. Okay, let's look at the explanation together. Now, to determine the probability that a molecule occupies a single position, we can divide the number of available molecules by the number of available positions, which is what N over V, just like we have seen. All right. Now, if we add more water to the flask, what it does, it increases the number of available positions. And if it increases the number of available positions, it simply means that more molecules have more places to be in, and which reduces the chances of effective collision, thereby reducing the concentration of the molecule. So the probability that a molecule is at site A, we have just said, is the number of such molecules divided by the available positions those molecules can occupy. And this is what we call the concentration of the molecule. Now, We are not concerned about the number of molecules or the number of available positions the molecules can occupy. What we are interested in is that ratio, the ratio of the number of molecules to the number of available positions. That ratio is what we call the concentration. So let's look at this. So we can say that the concentration of a molecule B is represented by the number of individual molecules of B divided by the number of available positions such molecule B can occupy. Alright, so let's continue. In order for two molecules to react with each other, they have to be at the same position at the same time. Now, the concentration tells us the probability that one molecule of a particular type is at a particular location. Don't forget that. So, look at this question. What is the probability that a molecule of B and a molecule of C are both at site A? That site A is just a given position of reference. Site A could be anywhere. Alright? So, what is the probability that a molecule of B and a molecule of C will be at the same position? So, the correct answer is the probability of B being there multiplied by the probability of C being there as well. And that's this option. So let's look at the explanation here. So since we are trying to determine the probability of two events, that's the coincidence of molecule B and C being at the same position or site A, we need to find the product of the individual probabilities. So the probability of coincidence will be probability of B multiplied by probability of C. So now in this context, in the context of chemical reactions, we need to know how likely is that the two molecules will be at the same position, right? So that is that probability of C multiplied by probability of B. So let's continue. Now let's be clear, there is nothing special about that site A. Like I have said, that site A could be any position within the volume of the flask. Alright, so but what applies to site A applies to any other position in the flask. Good. Now look at this question. Suppose there are 500 molecules of B and 500 molecules of C randomly distributed among 1,000 locations in the flask. The question here is, how many collisions do you expect to occur in the first moment if the molecules are truly randomly distributed? So, like I said, if the molecules are to be truly randomly distributed, the number of collisions will be the probability of molecule B multiplied by the probability of molecule C, which will give us the probability of what collision first. Now, that probability of collision multiplied by the total number of available positions of collision will give us the answer we require. Now let's look at the explanation. So, given the numbers in the question, the probability of a single collision between B and C at site A will be probability of B multiplied by probability of C, which is 1/2 times 1/2. 1/2 of which is 1/2 for probability of B is number of 500, the 500 molecules of B divided by the number of positions those 500 molecules can be, which is over 1,000. So 500 over 1,000 gives us 1/2 for the probability of B, which means the concentration of B. So the concentration of B is half. The concentration of C is half. Now multiply the two of them. The concentration of the both of them is 1/4, as the probability of both of them colliding is 1/4. So 1/4 multiplied by the total available volume, which is 1,000, will give us 250 collisions. Alright, so that is that. Now taking it a step further, now The question here is this: in that first moment, that means in that first moment of 250 collisions, how many reactions between molecules of B and C do you expect to occur? Remember, I said before that not all collisions result to an effective chemical reaction. So some collisions are ineffective because some collisions might not occur at the right amount of energy and at the right orientation. So there should be less than 250 collisions. So the answer should be less than 250 collisions. So let's submit and continue. See, that's correct. Less than 250 collisions. So let's go ahead. Now, not all reactions are created equal. If we set up two different reactions and put their reactant molecules at the same concentration, it's possible for one to proceed very quickly while the other proceeds very slowly, because there are several factors involved for a chemical reaction to occur. Let's continue. This is because a collision is only one part of a successful reaction, right? The other piece of it is ensuring that the molecules collide with enough speed and in the right orientation to cause the transformation. While we can think about the number of collisions in a purely probabilistic way, details of successful reactions depend on the speed of the collision and other quantum mechanics, which we might not discuss in this topic right now. But let's continue. Nevertheless, we can capture this information in a single number called the rate constant K. And this rate constant is a gauge which shows how likely it is that a collision between two molecules will result in a reaction. The number of reactions that happen between molecules of B and C per second will be probability of B multiplied by probability of C multiplied by the rate constant K. Alright, so this will show us the number of reactions per second that can happen. So K multiplied by B multiplied by C. So this is where K comes in. Let's continue then. So some reactions, like the combination of two reactive molecules to form the explosive TNT. TNT is called trinitrotoluene. So some reactions will happen with the slightest collision, while other reactions between styrene and propylene to form a plastic polymer requires many collisions before one will succeed. So that shows you that different reactions can occur at different rates. Alright, suppose we use the same conditions to run two molecule reaction between B and C. The reaction proceeds at the same rate. The reactions between B and C proceeds at the same rate. So the rate of reaction between B and C will be the probability of B, or the concentration of B multiplied by the concentration of C multiplied by the rate constant K. Everything will give us the rate of reaction of the two molecules. When we run this same reaction in a flask with 10 times much water, what do you expect to happen? So when this same reaction occurs in a flask with 10 times much water, that simply means that the volume has increased. So these molecules are now more widespread, making it possible that they cannot be able to collide with each other more frequently as they used to be before, because the volume is now 10 times much bigger. So what do you think that will happen? So will it stay the same? No, of course. Will it fall by a factor of 10 or will it fall by a factor of 100? Now, the correct answer is that it's going to fall by a factor of 100, and we are going to look at the explanation to that. Now, what is the explanation to this? Let's look at it now. So now, since increasing the volume of water tenfold will decrease the concentration of each reactant by a factor of 10, the product of their concentrations B and C will decrease by a factor of 100 because we are multiplying them together. So it becomes a lot less likely for the two reacting molecules to encounter each other when they each have many positions available. So that is that. So this thing shows this picture here shows the reaction. The molecules initially, when they were smaller in a given confined volume, they can react more. But when you increase the volume more, I can see 10 times more, they will find it difficult to collide effectively. That is what this is trying to show us. Let's get back to the problem. So, all right, as one more example before we go. Suppose a reaction requires 3 molecules of A to come together to produce a trimer. I mean, suppose for a reaction to occur, 3 molecules combine together to form 1 molecule. How will the rate of the reaction R depend on K and A? So this is the actuals. This is the correct formula for that. So let's look at it again. So the reactions that require more than 2 molecules to be in just the right place at the right time, they are rare. So compared to 2 molecule reactions, they require higher concentrations. Alright? So yet even these few and far between reactions follow exactly the same rules. Of course, we multiply the different concentrations and multiply also the rate constant. Okay, everything will give us the rate of a chemical reaction occurring. All right, so that is that. So this is it. Multiply the individual concentration of the reactants A, then multiply with the rate constant K here, as you can see, and then putting everything together give us a reaction rate. Okay, that's it. Let's go back to the problem. All right, so in this lesson we use the simple model of a chessboard to better understand how the likelihood of a chemical reaction between 2 molecules can be described in a quantitative way. All right, so this is also a way to explain chemical reactions in a probabilistic way. I hope you've enjoyed this lesson so far. Don't forget to hit the like button and the subscribe button, and also turn on the bell icon for more notifications when I upload more videos in this exclusive chemical reaction series. All right, let's continue. So there are other kinds of reactions though, all right, as we can see as we delve further in this series. So a single molecule can break apart to form many molecules, and in such a way large excess energy is given off. Right. So 3 or more molecules may also come together to react. So in all these cases, the same rules apply. But how can we envision the rate expression how we can look at the reaction rate will be different for each scenario. All right, let's review and reflect. So in this lesson, we use a chessboard model and probability to derive the reaction rates of chemical reactions. This is a powerful predictive tool that can help us determine when a reaction will proceed apace and when it will advance slowly. All right, we've come to the end of this lesson. Thank you for being here with me. All right, see you in our next lesson.